Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we're going to be doing a deep dive into a topic that's really at the heart of modern physics. We're looking at mass energy and nuclear binding energy from the unit on nuclei. And our goal is pretty simple, actually. We want to make sure that by the end of this, you understand exactly why the nucleus behaves the way it does. No confusion, and in a way that is totally exam safe. So let's start with a question, a simple one. Just look up at the sun. I mean, it's been shining for what, 4.5 billion years?
Billions of years, yeah.
A normal fire, like a petrol engine or something, it runs out of fuel in a few hours max. Why doesn't the sun just burn out? And more than that, why is the energy it releases so much more powerful, millions of times stronger than any chemical fire we can create?
That is actually a very good point. The scale is just, it's hard to grasp. In chemistry, we talk about electron volts, EV, for chemical reactions. It's all about electrons changing orbits.
Mm-hmm.
But here, the energies are so much bigger, so we must be tapping into something completely different inside the atom, right? Something much more powerful than just shuffling electrons around.
Exactly. You've hit the nail on the head. And the surprising fact is this, and you should really let this sink in. The sun is converting about 4 million tons of its own mass into pure energy.
Wait, 4 million tons?
Yes, 4 million tons. Every single second. It's happening right now. Every bit of light and warmth you feel from the sun is the result of mass literally disappearing and turning into energy.
Wow.
And that idea that mass can become energy is the absolute key to understanding the nucleus. Okay, so let's get to the core idea. It's called mass defect. And it's actually quite simple when you first hear it. When you take the individual parts of a nucleus, the protons and neutrons, and you bring them together to form a nucleus.
Okay.
The final nucleus, the assembled one, always weighs a tiny bit less than what you started with. The sum of the parts is more than the whole.
So if I take 8 protons and 8 neutrons, weigh them all separately and add it up, the final oxygen-16 nucleus will weigh less than that total. Some mass is just gone.
Exactly. The mass is missing. And to understand where it went, let's use a quick analogy. Imagine you have, say, 100 rupees worth of Lego blocks, separate pieces.
Okay.
Now you spend some time and energy to click them all together into a really stable, complex model. If you could somehow weigh the value of that final structure, you'd find it's only worth, say, 98 rupees.
So 2 rupees are missing. Where did they go?
They didn't just vanish. That 2 rupees was converted into the locking energy, the energy that holds all those Lego blocks together so tightly. That missing mass is what we call the mass defect, and its energy equivalent is the binding energy.
Ah, okay. So the missing mass becomes the glue. But why does forming a nucleus release energy in the first place? Why does it become more stable when the parts come together?
That's a fantastic question. And for that, we need a mental image. I want you to picture a very, very deep well.
A deep well, okay.
Imagine the protons and neutrons are all separate, sitting at the top, on ground level. They have high potential energy. When the strong nuclear force pulls them together, they fall, whoosh, deep down into this potential energy well.
And when something falls, it releases energy.
Precisely. As they fall into the well, they release a huge amount of energy. That's the binding energy. And the deeper the well, the more energy is released and the more stable the nucleus is. It's now very difficult to pull them back out.
So a super stable nucleus like iron means its nucleons have fallen into an incredibly deep well. And to break it, you'd have to provide all that energy back to lift them out.
Perfect summary. You have to supply the exact same amount of energy to climb out of the well as was released when they fell in. Stability is just a measure of the depth of that well.
So does this mass loss happen in chemical reactions too? Like when water is formed?
It does, technically, but the energy involved is, 1 million times smaller. In a chemical bond, you might get maybe 5 electron volts. If you calculate the mass for that using E equals mc squared, the amount of mass is so tiny you could never, ever measure it.
Ah, so it only becomes noticeable at the nuclear level with millions of electron volts.
Exactly. Only in nuclear physics does the mass defect become a real measurable number. All right, now that we have the concept, let's build the technical bridge. We need the formal, exam-safe language for this. It all starts with that one famous equation. Could you please read the relation given in our insert source?
Of course. It says, Einstein gave the famous mass-energy equivalence relation E equals mc squared, 13.6.
Thank you. The foundation of everything we're discussing, E is energy, M is mass, and C squared is just this huge conversion factor. It tells you that a tiny bit of mass is worth a tremendous amount of energy. Now, using that, we need to formally define the missing mass. So could you please read the definition for mass defect?
Yes. It is defined as the difference in mass of a nucleus and its constituents, delta M, is called the mass defect, and is given by delta M equals ZMP plus A minus Z, MM minus M, 13.7.
Excellent. Now, that equation might look a bit complex, but it's just telling us what we already discussed.
Okay.
Step 1, that part in the square brackets, ZMP plus A minus ZMN. That's just the theoretical mass. You're just adding up the mass of all the protons and all the neutrons as if they were separate. It's the before picture.
And then you subtract M, which is the actual measured mass of the nucleus, the after picture. So it's just
Wow.
mass of parts minus mass of the final phase.
That's it. And that difference, delta M, is the exact amount of mass that got converted into energy. Scientists use very precise instruments, mass spectrometers, to measure that M value very accurately. Step 2, we take that delta M and we plug it into E equals delta MC squared. The energy you get is what we officially call the binding energy, or BE. Now, step 3, this is important for comparing different atoms. A big nucleus will obviously have a huge total binding energy, right?
Well, yes. More particles means more glue in total. So it would take more total energy to break it all apart, even if each bond wasn't that strong.
You're one step ahead of me. That's exactly why we need to normalize it. We calculate the binding energy per nucleon, which is just BE divided by A, the total number of nucleons. The rule is simple. The higher the BE per A, the more stable the nucleus. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Okay, let's make this concrete with a quick example. Let's take oxygen-16. From experiments, we know its mass defect, delta M, is about 937 atomic mass units, or U.
And in our exams, we're always given the conversion factor for U, that 1 U is equal to 931.5 MeV per C squared.
Correct, so we just use that. The total binding energy, BE, is simply 1.137 U times 931.5 MeV per U. That gives us about 127.6 MeV. Just pause on that number. 127.6 mega electron volts. A chemical reaction gives you a few electron volts.
The difference is huge. It really shows how much stronger the nuclear force is compared to the electromagnetic force that's responsible for chemistry. It's a different world.
It really is. So that's the total energy. Now, for stability, we find the BE per nucleon. We take 127.6 MeV and divide it by the 16 nucleons in oxygen. And what you get is around 7.98 MeV per nucleon. That's a very high number. It means each proton and neutron is locked in that potential, well, very, very tightly. And this whole idea, this curve of BE per A, it directly explains nuclear fission and fusion.
Because everything wants to be more stable, right? Everything wants to get to the highest BE per nucleon value.
That's the driving force of the universe. The curve of stability peaks at iron 56 with about 8.8 MeV per nucleon. Iron is the most stable element. So light elements like hydrogen are on the left side of the peak. They can fuse together to form heavier things like helium, moving up the curve towards iron and releasing energy. That's how the sun works.
And heavy elements like uranium must be on the other side of the peak, the right side.
Exactly. They are past the peak of stability. Their BE per nucleon is lower, around 7.6 MeV. So for them, the most stable thing to do is to split apart fission into smaller nuclei that are closer to iron. Both fusion and fission are just nuclei trying to become more stable. Okay, let's shift gears and talk about some silent killers. These are the common misconceptions that can really cost you marks in an exam. Number 1, the term binding energy. Because it has the word energy in it, students often think it's some kind of energy that helps break the nucleus apart.
I can see that. I think I even had that confusion myself.
Yeah.
You supply energy to break something, so maybe binding energy is part of that process?
It's a very common trap, but the correct way to think is this. Binding energy is the strength of the glue. A high binding energy means you need to supply a lot of external energy to break the bonds. So high BE means high stability. It's the resistance to being broken. Misconception number 2. Students see mass disappearing, and they write that the law of conservation of mass is violated.
But that's not right. Mass isn't destroyed, it's
Right.
just converted. Mass and energy are two forms of the same thing.
Exactly. The correct statement is that mass energy is conserved. Mass on its own is not conserved in nuclear reactions, but the total mass energy of the system is always constant. And the third one, which we touched on. Students assume that since uranium is so big and heavy, it must be the most stable nucleus because it has the highest total binding energy.
Right, but we know the real measure of stability isn't the total. It's the binding energy per nucleon.
And that is the key. The true king of stability is iron 56 because its BE per nucleon is the highest. Please remember that for your exams. Iron 56, not uranium. To make sure all of this sticks, let's use a couple memory anchors. First, a simple phrase to repeat in your head. Mass lost equals energy gained. Binding energy is the glue. The stronger the glue, the harder to break.
Mass lost equals energy gained. The stronger the glue, the harder it is to break. That's good. It connects the two main ideas.
Now, for a physical gesture, I want you to actually do this. Hold your hands far apart. This represents separate nucleons, low binding.
Okay, hands apart.
Now, bring them together fast with a whoosh sound and clasp them together tightly. That whoosh is the energy being released. That tight clasp is the high binding energy.
Okay, got it.
Now, try to pull your hands apart. Really resist it. Feel that strain, that effort you need to separate them. That is the binding energy. That resistance is what makes a nucleus stable.
I can actually feel that, the struggle to pull them apart. That's the 8 MeV per nucleon we're talking about.
Yep, exactly. It's the work you have to do. If you remember that feeling, you'll never confuse binding energy with a force that breaks things apart again. So, to wrap this all up, let's do a quick 3-point summary. 3 exam-safe facts you must know. 1. Mass defect, delta M, is the real measurable difference between the mass of the separate nucleons and the mass of the final nucleus. 2. Binding energy, BE, is simply the energy equivalent of that mass defect. Calculated using E equals delta MC squared, it's the energy needed to completely pull the nucleus apart. And 3. The true measure of nuclear stability is the binding energy per nucleon, BE upon A. This value peaks at iron 56, making it the most stable nucleus in the universe. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSAM, right?
Yes, PROFSAM.com. We hope this has really cleared up any confusion about mass energy and binding energy for you. Thanks for joining us.